Right, we're going to do change a variable. Essentially, it's a technique for finding double integrals. There is an expanded version of this for triple integrals, but you would need to know how to find the determinant of a 3x3 matrix, which is not easy unless you've done linear algebra. And theoretically, you can actually do a 4, 5, or 6, but it becomes really kind of impractical after a while. So I've kind of broken down the first part of today into the skill building things, the things you need to be able to do to actually do change of variables. So we're not actually going to do any double integrals for the main part of today. We're going to be looking at how do you find an image of a region when you do a change of variable on it, how to find what are called Jacobians, and I'm going to show you a nice trick called a linear shortcut, and how to find Jacobians when they're not linear, which is basically the normal way of doing them anyway, but we're going to look at them in two different groups. The shortcut is really very helpful to just make your life easier. But if you don't like the shortcut method, then you can use number 3 for everything, and that will work. So, first guy I'm going to look at is how do you convert a region from UV space to XY space, because that's really what change of variables is like. So I want you to imagine that I've got a region S in UV space, and it's basically just that guy. Now, if I draw what that guy would look like, this would be typically U, this would be V, and U goes from 0 to 2, and V goes from 0 to 4. If you put the whole package together, would you agree that that region essentially describes a rectangle? Now, a couple of little things they don't spend a lot of time in this book on, and they should, is that when you go round a region, there is a convention for the direction. Do you notice that you go round anti-clockwise? Is there anything else that you've seen in math where you go the wrong way, anti-clockwise?
Unit circle.
Yeah. So that anti-clockwise thing is connected to that, right? That's just the way that you have to do it to make the math work, right? Now, suppose I have a change of variable. Suppose I tell you that x is 2x plus y. Sorry, that doesn't make sense. That x equals 2u plus v, and that y equals 3u plus 2v. And we're being asked to change this UV space in this region into what it would look like in the XY world. And there are two ways to do it. The first way is the way the textbook shows you, and good luck with that. And the second way is to realize that since these are linear, and the only ones you're really going to deal with are linear, we can do a kind of abbreviated version. What do I mean by that? Well, if you start at the origin and then you work your way around it, do you notice that the only places that really matter are the vertices? So I'm going to take each one of these vertices and I'm going to find out what they would change into, right, in XY space. So the starting point, I'll call that guy number 1, right, has coordinates 0, 0 in UV space. Well, 2 lots of 0 plus 0 gets me 0 for the x value and 0, 0 for the y value. So that guy ends up being here. So far, so good. All right, let's take the second corner, right? Because you're going this way. Wouldn't this be corner number 2, vertex number 2? And for vertex number 2, it has coordinates 2, 0. Well, what does that become? 2, 0. 2 lots of u, that's 4 add nothing, so you get 4. And what does a 0 get you? 6 add none gets you 6. So this guy becomes 4, 6. And now we are looking at number 2. So he goes there. Can you see what's going to happen with the next 2? I should go through them anyway. I randomly picked these, which is very dangerous. I've got a horrible feeling I might end up with a straight line if I'm not careful. But what should happen is it should go doink, 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 right? It should just be 4 corners that you kind of join up. So the third one, which is up here, has coordinates 2, 4. That's in UV space. And in XY space, 2, 4. 2 lots of 2 add that one gets you 8. For this one, 6 plus 8 gets you 14, which is okay. There is a bit of a bend in it, right? Last guy, this fella, his coordinates is 0, 4. 0, 4 gets you 4. 0, 4 gets you 8. And 4, 8 is where? 4, 8's about here. And then come back home. So that rectangle turned into this, I don't know, it looks like a bit like a rhombus shape. Are you comfortable with take the corners, use this to convert them to X, Y, Z's, plot the corners one at a time, corner 1, join it to corner 2, join it to corner 3, join it to corner 4, and then finish off by going back to the last point, and you've now got your region. In the homework, it just gives you 4 pictures and you pick the right one. Are we okay with that process? Right. Now, there is another way you can do it. Go look at the textbook. Essentially, you find the equation of the 4 lines and their start value, and you'll essentially end up with the same thing. Now, as long as it is linear, what I've just did worked perfectly fine. And since that's the most likely questions you're going to see, I think it's worthwhile. Do you want to see another one of this process, or is one good enough? Good enough? Okay, we'll move on then. So we're now going to find a guy called a Jacobian. I'll show you how they're written down. It's a kind of weird notation, but if you look at it, it kind of looks like 2-dimensional differentiation. That's about the closest description I can give you. So they're going to be 2 variables, x and y, both being differentiated with respect to 2 other variables called u and v. Now, for this particular question to have any relevance, then I keep doing that. You need to be told what x and y are in terms of u and v. Now, the formula for a Jacobian is it's a determinant. Just checking this one out. dx by du, dx by dv, dy by du, dy by dv. And have you seen that vertical line, the 250 people amongst you have, right? Isn't that the determinant of a 2 by 2 matrix? Now, in this question, put a little bubble around that guy. Differentiate that with respect to u, differentiate this guy with respect to v, differentiate this guy with respect to u, and differentiate with respect to v. Do you see if the things are linear? And what I mean by linear is there's no u squareds, no x squareds, right? It's all u's and v's and x and y's, right? Everything's single powers. That's what I mean by linear. This is the Jacobian. And this guy is 3 times 2, take away, right, major diagonal, 3 times 2, subtract minor diagonal, which is what? 4 times negative 2. In this case, it's 6, add 8. And so I believe the answer is 14. Are we good? Right. Now, if you are given the information this way around, isn't this pretty straightforward to get a Jacobian? Right. But this is more realistic. Wouldn't you expect a u sub and a v sub to be in terms of x's and y's? Now, how do you get the Jacobian of that guy? Well, there are 2 ways. The first way is you solve for x and y. And the second way is the linear shortcut. You want to see the shortcut, don't you? Well, I'm going to do the long version first, and then you're going to really appreciate the shortcut. So I'm going to call this equation 1 and this equation 2. I want you to think of u and v as if they were numbers like 5 and 6. Isn't this a system of equations then? The only difference is that when I solve it for x and y, I won't get x as 4 and y as 2, which is what you typically get in Math 94. I'm going to get x as a function of u and v, and so is y. So as I look at this particular combination, in fact, I'm going to rewrite them because I want to keep things above each other. Here is the first equation. I'm just rewriting it. Equation 1. Here's equation 2. And I'm going to use what's called the addition method. So I'm going to take equation 1, multiply it by 5. That's going to get me 5u equals 15x, take away 10y. And I'm going to take equation 2, this equation, and I'm not just going to multiply it by 2, because if I did that one, I just get negative 10y. I'm going to multiply it by negative 2. So that gets me negative 5v, negative 8x, plus 10y.
Wouldn't it be negative 2v?
Thank you. Yes. The other 2 are good. Can you see why I chose to make it negative 2 inside E2? Because in the addition method, don't you want one of these variables to be the same amount, but 1 plus and 1 minus? Which means I can now add them. Which gives me 5u take away 2v is equal to, what's that, 7x? And that can then get me x. Okay, I now know what x is in terms of u and v. How do you think I'm going to find y in terms of u and v?
Plug that back into the equation.
Right. It really doesn't matter, does it? This one, yeah, that one, or that one. You're not going to pick these because they're smaller, right? So I'm going to substitute the fact that x is 5/7 u, take away 2/7 v, and I'm going to plug it into, what do you want, number 1 or 2? Doesn't matter, but which one do you want?
1.
Let's do 1.
1 will do. So u is 3x take away 2y. U is 3 lots of this. Take away 2y. That's 15/7 u, take away 6/7 v minus 2y. What do you think I'm going to do next?
Get y by itself.
Okay, so if you subtract 15/7 u from 1u, you're left with negative 8/7 u. Check that, 1, take away that, 8, 7, yep. And add a 6/7 v to both sides. You now get that guy. And then can't I divide everybody by -2, which means this now becomes positive 4/7 u, and this becomes negative 3/7 v. Are we happy about that guy? Now we still haven't got the Jacobian, but at least we've now got it in the form that we need to get the Jacobian. So I'm just rewriting them together like this, provided I didn't screw up at least. So far, so good, right? Okay, Jacobian. Do that with u, do the x with v. Do the y with u, do the y with v. That's going to get me, well, differentiate this with u and all you get is 5/7, because that's 0. If you then do it with v, you get negative 2/7. You do this with u, you get 4/7. And you do this, you get negative 3/7. Major diagonal is 5/7 times negative 3/7. Subtract minor diagonal, negative 2/7 times 4/7. That's negative 15/49. Add 8/49. And that get me, I believe, negative 7/49, which gets me negative 1/7. Quite messy. It's not hard, I guess, but isn't it quite long and messy? Now I'm about to show you the shortcut. Same question, shortcut. Right, we already know the answer, right? The answer is negative 1/7. So let's see how the shortcut works. We have u equals this fella. We have v equals this fella. And I am going to find a different Jacobian. Now, do you notice I've switched places? It's uv over xy instead of xy over uv. Right. Now, 3, -2, 4, -5. Major diagonal, -15. Take away -8. And that guy gets me negative 1/7. Negative 7. And now the trick. The Jacobian that I do want, which is this one, is 1 over that Jacobian. Kind of cool. And if you think about it, it kind of looks like it should be true, doesn't it? Only works for linear, so don't try this shortcut anywhere else.
So, like with the squares, it doesn't work.
Yeah, unfortunately. But the vast majority of your questions, not all of them, but the vast majority of them are linear. So it'll work for them. You know, anything that helps reduce your workload, right? Now, if you don't like my linear, just do it, you know, the way you're going to do all of them. So third guy in the list, how do you find a Jacobian when it's a non-linear situation? Well, suppose I tell you that x is u squared plus v squared, and that y is u squared take away v squared, which is actually not that unusual, a Jacobian transformation. Well, the information is given exactly the way you want it. So you really won't spend too much time.
Shouldn't the x's and y's be in the numerator?
Darn
the
it in
derivatives
space.
and-
You're right. You're right. Do you know what? My brain is still thinking of the previous question. World Cup. Right, let's. Right. Yeah. Right. Differentiate with respect to u, you get 2u. Differentiate with respect to v, you get 2v. Differentiate with respect to u, you get 2u. Differentiate with respect to v, you get this guy. Major diagonal is 2u times negative 2v. Subtract minor diagonal 2v, 2u, and I believe you get negative 4 uv.
Shouldn't that be -8?
Did you all catch that deliberate mistake? You know, I've given up saying that statement. I should bring it back. Okay? Deliberate mistake. Just to make sure that you're all paying attention. The rest of you saw that, but you just knew what it was and wrote the right answer down, right? Okay. Let's try another basic Jacobian, right? And just so that we don't get too caught up with the only variables in town are u and v, let's do that one. Wait a minute, have you not seen that guy before? Who is he?
That's the conversion to polar coordinates.
Right. When you did the conversions to polar coordinates, wasn't there a funny little R that just kind of appeared from nowhere? And I said, look, it's there, trust me, you know, it has to be there, right? Remember that R? Wouldn't it be nice if we could figure out how it came about, where it comes from? Do you know it comes from the Jacobian? So, this time I'll try and do it the correct way around. Okay. So that's going to be the derivative of x with respect to r, then the derivative of x with respect to theta, and then the derivative of y with respect to r, and the derivative of y with respect to theta. Right, if you take r cos theta and you differentiate it with respect to r, what do you get?
cosine theta.
Agreed. Now, if you differentiate it with respect to theta, what does that guy get you?
Negative r sine theta.
Now, if you go this fella, you get a sine theta. And if you do this fella with respect to the other guy, I believe you get r cosine theta. Are you all happy about those four guys? Now, major diagonal is cosine theta times r cosine theta. Subtract minor diagonal, negative r sine theta times the sine theta. And we get r cos squared theta, two negatives make a plus, r sine squared theta. You see anything we can do?
Yeah, cosine squared and sine squared can go to 1.
So if we pull out r as a common factor, do you now see where that funny little r came from? That is basically where the Jacobian's going to go for all the questions we're about to do. Now, do you know that means you could invent your own coordinate system? Isn't this polar? Because it's got a name. But couldn't you invent a new coordinate system? Couldn't you do a coordinate system where it was r cos theta, but y was r squared sine theta? And that would generate a whole new way of looking at 2D space. And you could do equations that had x's and y's in them, right? Integrals with x's and y's and double integrals. And you could convert them into this new Robertson coordinate system. Now, why does that not work? Well, it does work, but why doesn't people give it a name? Because the only ones that seem to have been of any great use, right, the ones you want to use, would you agree polar gets used a lot with circles? And doesn't spherical get used a lot when there's spheres? And isn't cylindrical really just kind of using polar for part of its life? No one's really came up with. There are a few out there that we won't touch. For instance, there is an elliptical coordinate system where you actually use ellipses of different sizes and orientations to tell you where an object is. An elliptical coordinate system might be quite useful if you're dealing with planetary systems and movements, because those don't move in circles, don't they? Move in 3D ellipses. So you could imagine in a coordinate system where things were in terms of elliptical orbits, couldn't the motion of planets be described in 3D in a more concise way? So who knows, maybe one of you will invent a coordinate system that is really cool and can be used for double integrals that makes them easier. But what is it? 300 years of really cool mathematicians, none of them have come up with one. But if you used that attitude, wouldn't nobody ever invent anything? Because when Einstein done his special theory of relativity, couldn't people say, well, we've had 1,000, well, 1,000 years, we've had, what was Newton, 1690. Okay, we've had 300 years and Newton has been, laws of motion have been working fine. You're not going to come up with a new system. And then Einstein did. So who knows? Maybe there isn't a coordinate system out there that is just waiting for somebody to stumble across. Can you hear my dog barking?
Yeah.
Yep, Maggie, you are being a pain in the butt, young lady. Now don't give me those eyes. Go on, go and see mummy. Go on, come on, go. She gives me a look like I'm going to hit her with a stick or something. I've never hit her with a stick in my life. But it's that kind of big sad eyes, what you know, whatever. Okay, as always, I've completely screwed up my brain. Oh, we are finding Jacobian nonlinear. Right, let's try another one. And this is a version of question 3. X is going to be u squared plus uv, and y is going to be 9uv squared. While this thought is still in my head, I'll share it with you. When we do Jacobians, these guys here, when we use them, as you're going to find out in a little while, in double integrals, there is a convention that the Jacobian must be a positive term. Now, when the answer is u squared plus 2uv, we just call it that. But when you do linear, it is very often the case, isn't it? Probably half the time. Aren't you going to get Jacobian -4, -1/7? Those are going to be called 4 and 1/7 when we get to use them. So I thought I'd tell you that now in case you suddenly say, hey, how come its sign changed? The Jacobian is still -7, but the value that you use in the Jacobian is its positive number. And you will find that they stick an absolute value around it. 2 vertical lines, which I don't want to do because it distracts from this 2 vertical lines, and you get your guy. Okay, with respect to u, this guy gets you 2u, and this guy gets you v. With respect to v, you get u. This fella, if you differentiate it with respect to u, you get 9v squared, and with respect to v, you get 18uv. Hopefully I didn't screw up there. Are you comfortable with those 4 guys? If they're good, I'm moving on. Major diagonal then is going to be 18uv times that guy. Subtract minor diagonal, which is going to be this guy. What do I have here? 36u squared v plus 18uv squared. Take away 9uv squared, collect a couple of terms, 36u squared v plus 9uv squared. I'm quite happy with that, but if you're a purist, I guess you could do that, right? I don't think that's actually going to help you when you integrate. So you probably should just leave it like that. So do you feel comfortable about taking the corners of a region and just converting it to its new space in XY plane? How you find a Jacobian if things are linear? And how you find a general Jacobian in this format? Are we good to move on? I got 1 thumbs up. Yeah, I'm not going to do it with a 1 thumbs up because this is not good stuff. I got 2 thumbs up. That's better than I had. Come on, I want at least half of you to be okay with this before it's good. Okay, we got you. Yeah. Oh God, I'm getting everybody now. I think you're just joining in because you don't want to be left out. Okay, let's return. Let's give you the theory and then we'll start examples. Suppose I have a double integral of some function xy being integrated dx dy, and I don't know what letters of the alphabet, they keep changing them. I'm going to call it R, right? Got to call it something, right? So the double integral over a region R of some function xy dx dy. That will be converted into the double integral of a new region S. You know, like a rectangle turns into a parallelogram, whatever it is, right? So R turns into S. The function xy will be x of uv, comma, y of uv. I'll explain that in a minute. The Jacobian du dv. That little Jacobian guy, you see the vertical lines around it? That's the absolute value I was talking about earlier. Now that's only going to be relevant if this is linear and that's a number. So if the Jacobian is 5, it's great. If it's negative a seventh, that will become plus a seventh, right? That's the only little weird hiccup. Everything else is basically turned into u's and v's. So when I say x of uv, do you know that x is going to be a function of u and v and y is going to be a function of u and v, right? So that is basically what I mean by x of uv. And that guy there is what I mean by y of uv. So far, so good? Okay, let's move on then. Let's actually do a question. Let's find the double integral over a region R of 2 cosines of x minus y over x plus y dx dy. They're actually calling it dA, but I'll call it dx by dy, right? So far, so good? And we are going to do it over a region that is described by the vertices 1, 0, 5, 0, 0, 5, and finally 0, 1. So if I take this guy in xy space and I do 1, 0, 5, 0, 0, 5, and 0, 1. That's our world, right? This is the region R that they're describing. If that's a parallelogram, I better check my points. 1, 0, check. 5, 0, check. 0, 5, check. 0, 1, check. Okay, it's not a parallelogram. I looked at the wrong place. It's a trapezoid, which is okay because it is. These questions are going to be a little bit, what's the word I'm thinking of? They're going to be a little bit of art and not so much science. So there's a kind of intuition here. So step 1. You got to choose your U and V's, right? Why do you think I chose that?
Because that's in the first equation.
So picking the U and V's is basically a case of looking at your expression. Now, if they tell you who U and V is, that's great, but they probably won't, right? So picking it is a little bit of an art, right? You look at it. And you might say, well, what happened if I called this guy U and that guy V? Nothing. You get the same answer at the end of the day. Your math might look a little bit different on the road to the answer, but you get the same answer. So just pausing on this question, and I will come back to it, but let's just spend some time picking the U's and V's, right? I want to get good at how you would look at an equation that had a U and a V in it. So, I need a U and I need a V. Give me a U and a V.
U x plus y, then v would be x squared minus y squared.
Right? That's. By the way, this is question 13. Now, different situation. How you pick your U and V. Suppose we tell you that the region R is made up of those two straight lines. Obviously, that's the third one. So in these questions, it's the region R, or at least the boundaries of the region R, that tell you who you should use as your U and your V sub. If you rearrange this guy, what you get is 3x plus y equals 5. And if you rearrange this guy, you get negative 2x plus y equals 1. There's your U and there's your V. What about the 5 and the 1? They don't matter. Sort them out later. So sometimes the U and V are going to be in the equation. Sometimes the information for picking your U and V is actually going to be in the region. I got any others in here? Here we have a region described, oops, like that. Why do you think I might use this relationship? If I rewrite it as a third x and as a quarter y, does that help any?
Because they're linear.
They are linear. How are they going to play well with this then?
Square root.
They're going to actually end up generating a circle. We are really bad at integrating ellipses, aren't we? We're really good at integrating circles. So do you see what I'm getting at when I say this as an art? because there isn't one way to pick a U and a V. And there are lots of ways, depending on what information you've got to do that. So let's, oh God, time. Okay, I've got time to start this guy. And will you remind me tomorrow to finish this fella? So I'm just going to leave the region and call it S. And tomorrow we'll figure out what S is. It's going to become 2 cosine, U on the top, V on the bottom. You happy about that? Followed by the Jacobian, and then du dv. Okay, Jacobian of this question. Okay, differentiate that with x, differentiate that with y, differentiate this with x, differentiate that with y, and the answer you get is -2. So won't this be 2? So you're going to do 2 times 2, 4 times this fella, du dv. I know that's not pretty, but would you agree that that is at least doable? I can integrate this. You want me to do it? Right, for the short time we've got left, which actually, while I'm doing this, say hi. If you integrate that ugly cosine with respect to u, you will get 4 sine u over v. Will you get anything else? You do. Times what?
1 over v, right?
Yeah. And then you plug in whatever the things are and see what that turns into. But time has kind of overtook us. So we'll have to look at that in another day. Are we cool?
Wouldn't it be divided by 1 over v?
It would be
Would make it
multiplied by 1 over v. So let's find out why. Let's put numbers in. Suppose I said I wanted to do 4 cosine of u over 3. Then I'd get 4 sines u over 3. And then what would I multiply by? Isn't u over 3 a third? Oh God. Ah, you're right.
okay.